Okay, we have learned a lot about different types of functions in algebra. For 7.6, we're learning about exponential functions, and we're going to see specifically what those look like on a graph. Remember, a linear graph is a straight line. So these are not going to be linear. They are exponential, which means they're going to grow super rapidly or they're going to drop off super rapidly. So the definition of an exponential function is a function in the form y equals a times b to the x power. So a is going to end up representing your y-intercept, and b is going to be the, I'm just going to call it the pattern for now. We're going to see how that works here in a little bit, but y always stays y and x always stays x. So these are going to end up being different numbers. And by the way, if the y-intercept is ever 1, which it is here, and here, you actually won't even see it. It'll just look like y equals a number to the x because 1 will be hidden invisible, because 1 times anything is just whatever the anything is. So if you ever see, well, for example, if you see an equation like y equals 2 to the x power, that means there's nothing in front of it that's being multiplied for the y-intercept, which means it is 1. Okay, so this is one of those equations that you really need to memorize. It's as important as slope-intercept form or slope formula or point-slope form. This is the formula for an exponential function. Y equals, I'll even write it again, y equals a times b to the power of x. X is your exponent, which gives you a hint that it is an exponential function because it's in an exponent's location. Okay, these are examples. They're curved graphs. They're not linear. They're nonlinear. They're curved. This one, the pattern is increasing. It's doubling. So it's going up. First it started at 1, and then at the next one it's 2, and then at the next one it's 4, and then at the next one it would be 8. So they are growing exponentially. It's doubling every time. This one is a negative 2x, so it's doubling to the negatives. So it started at -1, it doubled to -2, then it doubled to -4, then it doubled to -8, and so on. So that's a -2 to the x power. 1/2 is not going to grow as rapidly. It's still going to grow rapidly, but it's increasing at a little bit lower of a rate. So it started at 1. Then it went to 2, and then it went to 4. So this is actually growing to the, do you see how it's going a different direction? A positive is going to grow to the right rapidly, and a half is going to actually come from the left and decrease. This is called a decay. So you probably want to write down that this one is a decay, so it actually would have started up higher. Sorry to confuse you. And it's actually dropping off as we go. It's cutting in half each time. First, the one that we could see is at 4, and then 2, and then 1, and then it's going to drop off completely. So it's going to go like this. A -1/2 is going to start higher, and it's going to go halves from the negative. So it's going to, the first one I see is -2, -4, and then it hits right here at -1, -2, and then at 0, -1. So you can see that it's cutting it in half each time. But it's getting closer and closer. What I want you guys to notice is this, decay, this one is growth. So you have exponential growth, you have exponential decay. So what I want you guys to see about all of these is that they're curved, and they also never quite reach 0. It probably looks like it does, but no matter how many times you cut a number in half, or here, this one's better. No matter how many times you cut a number in half, it's going to get closer and closer to 0, but it's just going to be tinier and tinier decimals. It's never going to actually hit the x-axis and be actually at 0. It's just going to be closer and closer to it. And that's what all exponential graphs end up doing. They grow super rapidly, or they drop off, they decay super rapidly, but they never quite touch 0. And that is important because it says x cannot equal 0. Or sorry, a cannot equal 0. Okay, so I want you guys first of all to identify the difference between linear and exponential functions. I already talked about how linear is a straight line and exponential would be a curved graph. But let's look at some other things besides graphs, like a table, for example. Before, when you have done a table, you have maybe noticed that it was like +1, +1, +1, and then you might notice that the bottom is also +2, +2, +2, or something. In an exponential function, we're not adding anymore. You can see that the common difference here to get from 1 to -1 to -3 is times 3. Times 3 again, times 3 again. So if you're not adding on both or subtracting, you are multiplying, which means there's a ratio. Instead of just an addition difference, there's an actual multiplication ratio difference. This is how you know it is going to be exponential. All right, on problem B, if you see an equation that's just a y equals 3x, there's no exponent, there's nothing exponential about this. So this is going to end up being a linear function. And the reason again is because there is no exponent. Oh, it says right here, linear, x is not an exponent. Okay, go ahead and pause the video and see if you can determine whether these two, A and B, are linear or exponential. Okay, the first one, the change is +1 on the x's, +1 on the x's, +1 on the x's. This one is +2, +2, so we're adding. Anytime you have pluses and pluses or pluses and minuses, you know right away that it's going to be linear because the change is constant. It says explain, I'll let you just say because the change is constant. This one, however, we can see that x is an actual exponent. So that means that this example is going to be exponential. Let's see if I can spell that right. There we go. This is exponential because x is actually in the position of an exponent, which is why it's exponential. Okay, let's practice a word problem. This is actually about flower beetles. So suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. That is why in the function there's a 2. That's the pattern. It's doubling to the x power. The function f of x equals 30 times x times 2 to the x power. And remember, 30 is your y-intercept. That's because we started with 30. That's our starting spot. And it gives the population after x weeks. So for x, we want you to fill in the number of weeks. How many beetles will there be after 56? I don't like how it switched it on us. You need to read carefully. Days. So we need to take days and we need to turn it into a number for x, but they want x in weeks. So I'm going to start by taking 56 days and dividing by 7 because there are 7 days in a week. 56 divided by 7 is 8. So we're going to plug 8 in for x because it's 8 weeks. So I'm just going to rewrite this function without the f of x. So 30 times 2 to the power of 8 weeks. All right, and remember, you always have to solve problems according to the order of operations, so we have to do exponents first and then go back and multiply. So don't call this 60 to the 8th power. You need to solve 2 to the 8th power and then go back and multiply by 30. So 2 to the 8th power is 256, and we're going to take that times 30. There's going to be a lot of beetles. 7,680. So there would be 7,680 beetles. So this is a major example of exponential growth. They started with 30, and after only 8 weeks, they're up to the 7,000s. So that is an example of exponential growth. Okay, let's go to the next page. Okay, the next page has a got it for you, so go ahead and push pause and try to figure out the population of rabbits. Okay, I hope you paid attention and read what it said because it said it wanted x representing half year periods, half years. So it says how many will there be after 3 full years? So if they want x to be in half years, and we're talking 3 years, we need to take 3 years and multiply by 2 because there are 2 half years in every year. So that would be 6. So we want to use 6 for our x. So we're going to write 20 times 3 to the power of 6. And again, I hope you did order of operations. You need to do your exponents first and then go back and times 20. Don't call it 20 times 3 and get 60 to the 6th power. That would be wrong. So 3 to the 6th power is 729 times 20. 729 times 20 is 14,580. 14,580 rabbits. Okay, let's look at how you would graph an exponential function. The first one is done for you, and then we're going to try a couple, but I want to remind you how to come up with your x values and then how to plug them in and solve to get your y values, which are going to turn into ordered pairs, which is how you graph. So I think a good standard choices for your x values are -2, -1, 0, 1, and 2. That just shows you on the x-axis how far it goes left and right to -2 all the way over to +2, just so you can kind of see where your graph is going to be between that domain. So when you choose your x values, you're going to do one at a time and you're going to plug it in for x. So remember, our x is an exponent this time. So what they did, and they showed you right here, they took 3 times 2 to the -2 power, because we're starting with -2 in for x. And you should remember from an earlier exponent lesson that you can't have negative exponents. So this whole term is going to flip to the denominator to become positive. So that's why we learn those rules, because we need to know them when we graph. So you've got 3 that can stay in the numerator and 2 to the -2, which flips to the denominator and becomes positive. So that'd be 3 and 2 squared is 4, so 3/4. So at -2, your y is 3/4. So they've turned that into an ordered pair, -2, 3/4. So they've graphed a -2 and about 3/4 of 1, not quite 1. Okay, and then you can see how they did their next one. -1 would flip to the bottom and become +1. 3/2 is the same thing as 1/2. So at -1, it's 1/2. So at -1, they went up 1/2 and put a dot right there. 0 is our y-intercept. So at 0, anything to the 0 power is 1. So 3 times 1 is just going to be 3. So 0, 3 is our y-intercept, and then they kept going and got 2 more points. So it should be a curved graph because it's growing exponentially, and that is what it's going to look like, and that's how to get your points. So let's try a couple of these. These are supposed to be got it's, so you can push pause and try it on your own if you would like, or if not, I'm going to go ahead and work these out with you. So I would suggest we stick with -2, -1, 0, 1, and 2. And I'm writing them down here so I can have a little bit of space up here to kind of work them out. So here's our equation. Y equals 0.5 times 3 to the power of x. And we're going to use these for our x's. So let's just start in with -2 for our first x. So we've got 0.5 times 3 to the -2. That's our first x value. So remember, you can't have a negative exponent. It's going to flip to the bottom under a 1. And now it's going to be positive. So this is the same thing as saying 0.5 times 1 to the 1 over 3 squared is 1/9. So I'm going to put that in my calculator. 0.5 times 1/9. 0.5 times 1 ABC button, 9th. That's really tiny. 0.0, I'm going to call that 56. 0.056. 0.056. And that is what we need to put here. So we're going to have a really tiny dot. This is going to show you exponential growth at a rate of tripling every time. Okay, our next one is -1. So we're going to put 0.5 times 3 to the -1. Again, you can't have a negative exponent, so it's going to be 0.5 times, it's going to flip to the bottom and become a +1, which is the same thing as 1/3. So 0.5 times 1/3 in my calculator is still tiny, but less tiny, 0.167. So it's about 0.167. So it's getting a little bigger, but still really, really tiny. The 0 is going to be our y-intercept, so I can go ahead and work it out for you to remind you how exponents work, but anything to the 0 power is the same thing as 1. So it's 0.5 times 1, which is just 0.5. All right, I'm almost out of space. I'm going to come over here for my positive 1. So 0.5 times 3 to the positive 1, that's just times 3, because 3 to the positive 1 is just 3. So 0.5 times 3, and that would be 1.5. And now lastly, let's put in a 2. So 0.5 times 3 squared. Exponents first, so 3 squared is 9. So I'm going to put in my calculator 0.5 times 9. 4.5. So this is growing extremely rapidly. In fact, I know we don't usually do one bigger, but I want to show you how quickly it's going to get really large. I'm going to plug in a 3. 0.5 times 3 to the 3. 3 to the third power is 3 times 3 times 3, which is 27. So if I plug in my calculator, 0.5 times 27, it is already 13.5. So look at what we've done in this pattern. We've gone from so tiny, it's less than 1/10, all the way up to 13.5 in just a few times of tripling. So let's go ahead and graph these. These turn into ordered pairs. So your first dot is at -2, and then so tiny you're not even going to be able to see it. It's not quite at 0 though. Remember I told you nothing is quite at 0, so it actually shouldn't be touching that 0 line, but that's okay. -1 and a little bit bigger, it's basically in the same spot. 0, 1 or 0.5 is right in the middle here. 1, 1.5 is right there. 2, 4.5, look how rapidly this is growing. It's definitely a curved line. And then I know this is going to be off the graph, but 3, 13.5 would be way up here already, just in the very next one. So think about where our even next one would be. It would be way, way, way up there. So let's draw a curved, soft line through it, and just basically arrows on both ends showing that it could have gone further down had I picked a larger negative, or it could have gone way up depending on how many I keep going up to on the x's. Okay, this got it is going to be exactly the same, but it's a -0.5, but otherwise these are the exact same. So you can take time to work it out if you want, but all it's going to do is stick a negative in front of all of these. So our answers are going to actually be the same. They're just going to be negative. So again, work them out if you need to. But when you multiply, you're going to square it first and then go back and multiply by this time -0.5. So it's literally going to be these exact same answers, except they're going to be negative now. So if I go -2, it's going to be, what do we have here? -0.056. -1 is going to be -0.0167. Oh, not a 0 in front of it. Sorry, didn't write that right. -0.167. 0 would be at -0.5. 1 is going to be at -4.5. 2 is going to be at negative. What did I do wrong? I left out 1.5. Sorry. Guess I should have worked these out. I'm just trying to look at my little table over here. -4.5 is next. And then I know we didn't go to 3's, but that would have been -13.5. Okay, let's look at how these look on a graph different. -2 and then really tiny. -2 and negative barely. -1 and still tiny, still basically right there. 0, -0.5. So 0 down 0.5. 1, -1.5. 2, -4.5. And then if we were to do 3, it was already way down here to -13.5. Okay, so again, we've got a curved line, but it's headed downward. All right. So basically, I want you to see that these are the same numbers, But if your A term is positive, you're going to have growth. And if your A term is, sorry about that, negative, you're going to have, it's going to drop off. You're going to have decay, or actually it's just regression down. Okay, so I pulled just a few problems to look at the very end of today's lesson, and these are problems that look a little bit similar to your homework problems, some Math Excel problems, and they're things that weren't necessarily in this video, but you're going to need to know how to do. So it says evaluate the function. We've done this with linear, but we haven't done this with exponential before. If they want you to plug in x equals 2, then you're just going to do 6 to the x is going to be a 2. So the exponent is going to be 2. 6 squared is 36 because 6 times 6 is 36. So that's the answer. In this equation, they want you to use 3 for the little x value here. So that would be 20 times 0.5 to the third power. This reminds me a lot of the Beatles problem we just did a little bit ago. So just remember to do order of operations. I think that's where it's going to maybe get you. So you need to do the 0.5 to the third power first, which is 0.125. And then go back and multiply that by 20. All right, 0.125 times 20 is 2.5. All right, so when it says evaluate a function, you're just plugging in whatever they say x is for x. Okay, the finance question, it gives you, this is exactly like the Beatles question. So it's giving you this equation, 5,000 times 2 to the x power. Oh, but be careful, x is the number of decades. Remember, a decade is 10 years. And it wants to know how much the investment is worth after 30 years. So if there's 30 years and there's 10 years in a decade, then you're going to plug in 3 for x, because we're talking about number of decades for x. So you will put 5,000, again, it's probably just trying to catch you and see if you're actually reading it, times 2 to the power of 3 decades. And again, order of operations, 2 times 2 times 2 is 8. Do that part first, and then go back and multiply by 5,000. 5,000 times 8 is 40,000. So this would be worth a $40,000 investment. All right, last one. They want to know basically which function has the greater value, if one of them has the greater value. Let's see, the first value is this, the second value is this, and they want you to plug in 2 for the x's and see which one will be bigger. So the first one is 4 to the x, which they want you to use 2. 4 times 4 is 16. Or is 2 to the fourth power bigger, because 2 is x. So 2 to the fourth power is 2 times 2 times 2 times 2, which is also 16. So in this particular case, which is greater, they're equal. So neither, I guess. So I think on Math Excel, they'll give you the option to put either neither or they are equal.